everyone, Katrina here. Today I'm going to tell you how to interpret different types of eigenvalues. Be sure to watch to the end so you can see all 4 different ways we can interpret them, and please subscribe for more videos. So the first type of eigenvalues that you can get are real and distinct eigenvalues. Remember that when we're solving for eigenvalues, we're simply solving the characteristic equation, which is the determinant of our matrix A minus our lambda times the identity matrix, and setting that to 0. So we're just solving for these eigenvalues. So they can also be considered as the roots of our characteristic polynomial. So just like any type of quadratic or cubic polynomial that you're factoring and solving for the roots, you can have real roots, complex roots, distinct roots, and repeated roots. So that's the same kind of situation that we have here for eigenvalues. So when we have the real and distinct roots, that means that our transformation is purely scaling, stretching, or compressing along independent directions. And these independent directions are our eigenvectors. So when we have real and distinct eigenvalues, we have linearly independent eigenvectors, and our transformation is simply just scaling along those directions. Okay, so let's look at another case. What if we have real and repeated eigenvalues? So that means they're still real, but we have more than one. And in this case, what if we still have full eigenvectors? Well, full eigenvectors means that the number of eigenvectors that we have, the number of independent eigenvectors we have, is equal to the dimension of our matrix. So that means that we have full rank. So in that case, it's just the same as our first case, and all we have is simply stretching and compressing along our independent directions. That's the key over here. We have to make sure that we have full eigenvectors in order for that to work. Okay, so what if we don't have full eigenvectors? What if we have real and repeated eigenvalues without the full eigenvectors? Well, in that case, we have something known as shearing. So that means when you have a shearing transformation, it moves the points parallel to one axis, and it does not simply stretch or compress along our eigenvectors or our principal components. So in this case, the matrix is known as being defective, and it's also not diagonalizable. Okay, the last case that we can have is complex conjugates. So just like I said, in our quadratic or cubic situations, we can have complex roots. So the same goes for eigenvalues. So this is a little bit different. So when we get complex conjugates, that means that the transformation is either a rotation or a spiral. So if we look at a complex conjugate, you always have some real part over here, where your A over here is your real part, and then your IB here, this is your imaginary part or your complex part. And what this means is that our real part scales along the principal component, so along the eigenvectors, just like our distinct real roots did previously. However, this imaginary part rotates our transformation. So it's a rotational transformation. So that's why this is pretty neat, is that sometimes you can just have it scaling the transformation, and other time you can have it rotating. And when it scales and rotates at the same time, that's when you end up with a spiral transformation. So these can have really cool artistic implications. So there's a lot of links between eigenvalues and arts and fractals, which I'll get into in some subsequent videos. But the main thing I wanted you to get out today is that there's 4 different types of situations that we can have. We'll go through a quick summary of them once more. So you can either have real and distinct eigenvalues, which means you're just purely scaling along your independent directions. If you have real and repeated, but with full eigenvectors, you're stretching and compressing just like you were before. However, if you have real and repeated eigenvalues without full eigenvectors, so that it's degenerate, that means that you're shearing, which you're moving points parallel to one axis. And finally, if you have complex conjugates, that means your transformation is a rotation or a spiral, where your real part represents the scaling and the imaginary part represents the rotation. So I hope this was helpful. I'll be following up with more examples where you can see this in action. If you enjoyed this video, please give it a like and subscribe for more. I look forward to seeing you next time.